In this episode of Voice of the Sea, we're investigating new, small-scale wastewater treatment systems that will help stop the daily leakage of 50 million gallons of sewage from cesspools across Hawaii. We'll see how engineers are testing locally sourced materials to help clean our wastewater, and how researchers are tracking the sources of pollution into the ocean. We learn about the installation of off-the-shelf solutions like self-contained aerobic treatment units. We start off talking to Dr. Judy Lemus during the installation of the first incineration toilet in Hawaii.
It's a very exciting day. We are installing a Cinderella incinerator toilet on Moku'oloi, which is the home to the Hawaii Institute of Marine Biology.
You mentioned that the toilet doesn't need any water connections, but it does need electricity, is that correct?
It does need a small amount of electricity. Right now we're using a gas incinerator, but the electronics are powered by a solar panel. So we're also not connected to any sort of power grid. We put the toilet actually in a shed that is movable so that we can move it to different locations on the island as needed.
So we have this unit, come on up in here. We have propane supply, power supply from the battery and solar, and air intake at the base. 4 lag bolts to hold the toilet down.
Uh-huh.
And let's go around back here real quick. You can see our solar panel. This is a supplied vent line. So when it incinerates, it pulls air from the intake down below here. Here we have the propane. And I'm told 40 to 60 uses for a 20-pound bottle like this, which is about 40 cents a use in Hawaiian cost for gas here. Absorbed glass mat battery. Very durable. And then our little control unit there, the SunSaver 10, which controls the solar panel. It's on a skid. I can take this with a forklift and I can move it anywhere I want.
What of what you just showed me would be necessary for a home installation?
Okay, well, I believe they have the electric model also, which you're going to need a vent pipe and you're going to need air intake. You would skip all the solar and the battery and the propane, and it would be wired with your household power. So it would be even simpler. We started the unit up and it's running. It's actually doing a dry run incineration cycle. Next cycle, we'll throw in an apple banana. And from what I understand, the bowl will hold about 100 flushes. So once a week, you empty the little bowl and it's just ash.
Are there any concerns about the temperature or hotness of the toilet? Could somebody burn themselves?
No, I've felt around the toilet. You can't feel any heat at all. It's all in an insulated burning chamber. So it'd be pretty hard to burn yourself.
And what about the noise? Is it loud?
No, it sounds like there's a ventilation fan in the toilet. It sounds like a solar 12-volt, 4-inch fan.
So when it runs through a cycle after you flush, how long does it take before it's ready for the next person to use it?
You can use it 4 to 5 times in an incineration cycle. So I can go in there. Let's walk around front again. This is a liner. The liner has to be used. I am interrupting the incineration process. Liner goes in right here, just like that. You do your business, close the lid, let it run its cycle. So as far as maintenance goes, this is certainly easier and more sanitary to clean than your household toilet.
They're recommending every 5 years there's a routine maintenance program. Rough estimate on the units is $5,000 to $6,000 to purchase.
If we can put in place systems that don't produce any waste other than a charcoal that is pure, that actually could potentially be used as a soil amendment, that charcoal production is just a fraction of what we normally as a society put into our systems, into our sewage systems.
You know, along with remote places like this where there's no sewage infrastructure, currently, you know, if they have a porta potty or something, you know, some of them pay $200 a week just to have them pumped. With the other cost of just renting the unit itself, this could pay for itself, you know, definitely in less than a year.
Next, we're looking at self-contained aerobic treatment units. The Kauai Beach Resort recently installed one of these ATUs to treat wastewater at the Nukuali'i Beach Park on Kauai's east side. The same type of ATUs are also available for residential use. We caught up with engineer Dennis Poma to learn more. So we have two ATUs, or aerobic treatment units here.
These are actually mini municipal wastewater treatment plants, very similar. Secondary treatment, it's considered secondary treatment, same that you're seeing in the upgrades going on at Sand Island or Honouliuli.
How big of a household are these rated for?
Right, so in Hawaii, our rating system is based on bedrooms, and it's 200 gallons per bedroom here.
So this is a 5-bedroom.
5-bedroom, both are
unit.
5-bedroom systems. The CE10 is a $12,000 system, and the CEN10 is a $16,000 system.
Can you talk to me about what they have inside and then maybe what differs between the two types?
Sure. They're both rated for 1,000 gallons or the same volume of wastewater to go through it. The difference is this one does not have the N, which is for nitrogen removal. They're both 3-compartmented systems. The first one is just a receiving chamber, or what we call a sedimentation chamber. The influent or the domestic waste comes in from the household into this chamber. And there's a baffle or a wall in between the middle chamber. And in there, the baffles allow the water to overflow into what's known as the anaerobic chamber. That's where we actually promote the decomposition of nitrogen. As it comes through, it then overflows through another baffle system into an oxidized state. And in here we have 2 types of proprietary plastic media that we're adding oxygen through diffusers and through a blower. So we're just basically creating an oxidized state inside. And as this stirs up, it promotes both your ammonia, nitrogen removals, also the biological oxygen demand and the organics, and then also your suspended solids. It actually gets recycled back, and it comes back into the first chamber. And at that point, when you have this highly oxidized water and it mixes with this anaerobic environment, that's where you get the decomposition of your nitrogen gases. And that's why in the N series, you're getting a much higher level of nitrogen removal. This gets down to 10 to 20 parts per million nitrogen, and this is getting you below 10. Because we're so close to groundwater, we're so close to surface water, it's really important to reduce that nitrogen compound. So this is obviously our largest system, but so it'll be a fairly big hole in the ground. The inlet pipe from the house will come from the house, and it'll go into the inlet in the system. As the water is processed through the system, it will exit the system, and it will then go to a leach field. And the leach field is generally today's technology are chambers, or called gravelous systems. So these domes that sit on top of the soil that allow the water to come in and percolate into the ground. About 25% of the units going in across the state are aerobic units. A lot of them are not necessarily required, but they're just individuals who want to be better for the environment, have better quality, and they're doing aerobic. So 75% of your upgrades are septic tanks.
The University of Hawaii's Sea Grant College program focused on Hawaii's coasts and its communities through sustainable development, safe seafood supply, sustainable coastal tourism, hazard resilience, and healthy coastal ecosystems. Hawaii's Sea Grant.
Dr. Roger Babcock is engineering locally available materials to build better leach fields for septic tanks in order to improve the water cleaning process in our backyards.
Sometimes things that we can't see are still a problem. So we do have high rates of staph infections and MRSA and things like that from swimmers and surfers in certain areas. And that is due basically to cesspools. It's not due to our treatment plants. They have a much higher standard of what they're allowed to discharge into the water. We need to take care of our water. We need to be sustainable and think about the future and greater populations discharging more and all that kind of stuff.
Can you talk to me about the role of engineers in designing and testing wastewater treatment systems?
Engineers, civil engineers in particular, are the ones who design wastewater treatment systems, including those that are used on site at individual homes. What we're doing is trying to develop some new low-cost passive alternatives to more expensive mechanical alternatives to upgrade cesspools. Cesspools date from the 16th century when they were started, and modern cesspools were from the 1800s. But we do have 21st century technology available for wastewater treatment, even at individual homes. And so that's important. We do need to upgrade our infrastructure. So what we're doing is what we call a passive leach field or a passive absorption bed. Basically, it's gravel or sand bed where slightly pretreated water from a septic tank is distributed, or water from an aerobic treatment unit is distributed, and it's there for infiltration. We're investigating a passive type system which has been developed and used in other places, but it hasn't been approved for use in Hawaii. It's not a patented technology, it's just a practice. And so with a practice, you need to have some experience, and so then you can develop design criteria. And then the design criteria would be in the state's rules. The idea is passive is great because we have all these systems that are going to somehow have to be managed. And if it's a more complicated system, that is costly, but there's lots of places where things could sort of fall off the radar. And we have 90,000 or maybe more systems that need to be replaced. And we don't have the management structure or systems in place that are big enough that could handle all those systems. Who's going to make sure these things are working?
And do you see these passive systems having a measurable benefit on our nearshore environment or our water resources?
Absolutely, yes. So there are certain areas, of course, where there's already documented impacts. So those would decrease or essentially be close to eliminated. But in all cases, it's going to improve the underlying groundwater and the nearshore waters. The other big hurdle that has to happen is these systems are not free. We're trying to make them low cost, but the costs for an average home for these 80, 90, 100,000 homes is $20,000 to $50,000. So that's a big deal. It's in all of our interests. It is a public good, that we upgrade these things. There's also a need to get started. We have 30 years till 2050 to get it done. But right now there isn't any trigger to actually make that start. So it seems like it's a far off problem that somebody else's problem, but we have to find a way to get this started because we'll learn from the process. There'll be economies of scale, technologies other new technologies that are going to come in, and et cetera.
Next, we're talking with Micah Tang about the experiment he's conducting to figure out the best materials for breaking down waste and removing nutrients. These layers of material can be paired with septic tanks to clean wastewater before it heads to our drinking water, our rivers, and the ocean.
I'm a graduate student. I'm pursuing my master's degree in civil and environmental engineering, where my research has to do with cesspool conversion technologies and wastewater treatment of on-site disposal systems. I started working on these columns in December 2019. They were already built by a student before me, so my job was to just keep them running and then to start analyzing the effluent that we got out of it. And then I'm building a bunch of new columns that have new materials. So instead of basalt sand and coral sand, we're going to be testing things like biochar and albizia wood chips, albizia sawdust. We're also using, instead of just a sawdust from plywood, we're going to try using wood chips. So all kinds of different materials we're trying and testing. What I have here is a new column. And this one is plexiglass, see-through, obviously. We're going to use these see-through columns to investigate anything that has to do with clogging inside of the columns.
And so if you were to summarize your preliminary findings, what are your conclusions so far?
We're achieving the nitrogen removal that we wanted, which is at least 50%. And then we're also getting phosphorus removal.
Are there particular materials that you think are more promising than others?
One that I think is most promising is the basalt sand, just because of its potential to remove phosphorus as well.
And why is removing phosphorus so important?
So phosphorus, like nitrogen, is another fertilizer ion that some people refer to it as, which can cause eutrophication in water bodies and toxic algal blooms, things like that, that contribute to fish kills and decrease in biodiversity.
We are looking for a few heroes, mentors, trailblazers, innovators. A passion to change lives, spark curiosity, open hearts, and awaken minds. Help students answer the question, who am I? This could be your calling, but this is no job. It's the journey of a lifetime. Be a hero. Be a teacher.
We're talking with microbiologist Dr. Craig Nelson about the tiny organisms used to help clean our wastewater.
The line that you learn when you first start studying what's called environmental microbiology, to separate it from sort of classical microbiology, which is all about us getting sick, is this concept called everything is everywhere. And the environment selects. Anytime you ask a microbiologist who works on environmental stuff, they're always thinking that. You can get any microbe you want. You just have to have the right conditions, and somehow they will magically show up. There's about 10 times more viruses in any environment than there are bacteria. In a gram of soil, there's 1,000 bacteria. That means there's about 10,000 viruses, just types of viruses. We don't really have control over these things. We just kind of have to do what we can to maintain biodiversity in the system at a reasonable level, and do what we can to kind of foster sort of a happy environment to get the microbes that are going to do the jobs that we need to do it without getting wiped out by a virus. And a lot of times specifically when you're trying to remove chemicals, nitrogen, carbon, organic matter, you actually want it to be simpler because, first of all, you can understand it better, you can control it better, and you can bend it when it goes out of whack. So if suddenly your septic system is not removing nitrogen anymore, it's not like, oh, there's 1,000 levers I could pull. It's like, well, I kind of knew that the only thing I'd given them was wood chips to eat. And so, if they're not removing the nitrogen anymore, maybe all I need to do is add wood chips, or maybe one of 3 or 4 more things I can do. And probably there were only 10 or 15 dominant bacteria in there because it's such a simple ecosystem. Whereas if you just dump it in the soil, it's like, well, it depends. A long time ago, there was no oxygen on Earth, and there was a huge diversity of microorganisms. And then at some point, 3 billion years ago, cyanobacteria figured out how to make oxygen. And so the organisms that use oxygen, they kind of all do the same thing. In fact, they do the same thing that we do, right? They do what's called aerobic respiration. When we eat a hamburger, we bring in oxygen to break down that hamburger. And all these microorganisms, you feed them sewage, and they bring in oxygen and they break down that sewage. And they do it really fast, and that's great. But a lot of the other things we want to remove from the sewage, nitrogen, sulfur, iron, a lot of those breakdown processes are actually really old metabolisms that animals and plants can't do. So we need to basically go back to the old Earth. And that's where all the organisms that lived and dominated before oxygen was in the atmosphere diversified, and they can breathe and eat all kinds of different elements. A lot of them breathe, instead of breathing in oxygen to break down organic matter, they breathe in nitrate. It's in the water, so they're not literally breathing it, but it's the same idea. They're bringing it in to carry out the reaction. And that uses up nitrate. So if you want to get rid of nitrate, you need somebody who breathes nitrate, and they'll break down the nitrate. And the only way to get those is with an anaerobic layer. If you have an area that's sort of polluted, you often see like a lot of algae growing. And yeah, our waste is full of what we just sort of loosely call nutrients. Things that algae need to grow: nitrogen, phosphorus, a lot of times iron. These are all things that are in our waste. And if we don't remove them through this wastewater treatment process, then we're going to be fertilizing downstream. And that's something we really want to avoid, because it leads to algal growth in coral reefs. It leads to phytoplankton in the water, which makes the water more cloudy. And then a lot of times when those things die and break down, they remove oxygen from the water, which kills fish. And so that's really negative. And so we really want to remove everything we can from the wastewater. And the best way to do that is to have a very carefully curated set of microbial assemblages. And it's not just one, right? It's like a little group of them kind of interacting together. But each of them is breaking down a different component of things that we don't want to send back out into the environment. So what we'd really like to be able to do, but instead of relying on these sort of mainland indicators, we'd like to really know what's in our sewage. And is there a way for us to measure something relatively easily in the coastal ocean to be able to say, it looks like there might be a little bit of sewage contamination.
And so you're sampling cesspools and wastewater effluent?
That's right. We are coordinating with a variety of homeowners in this area around Hilo to essentially ask if we can go and sample some of the cesspools, some of the septic tanks, and that way we can get an idea of what are the microbes that live in these different habitats, and is there anything in them that we can detect in streams or the coastal ocean that might be an indicator. So today, and in fact, I think when you talk to him, my graduate student, Nick Vanderzeel, will have finished a trip to the wastewater treatment plant.
My project it's like Hilo Bay, but it's also the coastal community of Keaukaha. It's called King's Landing, all the way to a popular surfing beach called Honolii that actually has one of the rivers in town feeds directly into this like super popular surf spot. So it's kind of obvious that area is kind of a concern for like what bacteria are growing in the water there. This project is in collaboration with UH Hilo, and we have 2 graduate students doing more traditional sewage pollution indicators, such as nitrogen 15 and algae, Bacteroides, Enterococcus, and Clostridium perfringens. While I'm doing more of like the community genomic analysis part of it. So that pretty much involves getting water, putting it on a filter, extracting the DNA from it, sequencing the DNA, and then instead of just like looking for one individual bacteria species, I'm actually looking at the whole community as into what's in there. We have the wastewater treatment samples. We're working on getting the cesspool samples, and we want to compare the wastewater treatment samples, the cesspool samples, and then the water samples that we're just getting from inside of this community to see if we can definitively say you're having like wastewater outfall pollution, or like a cracky sewage pipe, or this is cesspool pollution.
With more than 80,000 cesspools to replace in the next 30 years, Hawaii will need a variety of solutions to achieve its clean water future. Learn more at voiceofthesea.org. Follow us online at Voice of the Sea TV. Mahalo for watching Voice of the Sea. Exploring Our Fluid Earth is the dynamic curriculum developed by the University of Hawaii's Curriculum Research and Development Group. The award-winning Fluid Earth and Living Ocean textbooks are now interactive and online. New activities, updated content, and a teacher community. Exploring Our Fluid Earth is now freely available. Find out more at exploringourfluidearth.org.